This video is going to be on related rate problems. So related rates refers to when you differentiate a function with respect to time. So that might be like the radius of something is changing as time increases, or the distance between two things is increasing as time increases, or the distance is decreasing as time increases. But all of your rates of change are happening with respect to time. So this is how the variables relate to each other as time goes on. And the note that you want to write to yourself here is that we are going to use implicit differentiation every time. All right, so for example, if we wanted, this is an oversimplified example, but just so you can kind of see how this works. When we find the derivative of y, we're going to say the way that y is changing with respect to time. So we're going to say dy dt, or 1 dy dt, because the derivative of y would just be 1. And then the derivative of the x side would be 2x dx dt. So for both of these, or for any variable that shows up, we are taking the derivative of that with respect to time. So this means how the y is changing as time changes, how the x is changing as time changes. So they gave us in the problem that x equals 1 and dx dt equals 2. So that means we're going to go ahead and plug the 1 in for x and plug the 2 in for dx dt. And so that means that dy dt is 4. So the rate that y is changing would be 4 units, whatever those units happen to be. All right, so here are some helpful hints to get started. The first thing we want to do, since you guys are not scared of the word annotate, I'll go ahead and use it. So annotate the problem. So underline things that are important, highlight things that are important. Annotate and draw a picture. Second, we want to write down the given information. And identify what you're trying to find. Third, we want to find the equation or formula. So if they're talking about the increase of an area over time, or a volume over time, or a surface area, then those would be formulas that we would maybe be Googling to make sure that we remember. So find the equation or formula and take the derivative. And here, whenever you take the derivative, just like in that oversimplified example up here, every variable in the problem that you take the derivative of, you're going to use implicit differentiation. So I'm going to write implicit, and again, underline that, make it bold, put a star next to it, something to make sure that every single time you do the derivative in these problems, we always say the implicit differentiation, because we are relating our change back to the time that's passing. Fourth, we're going to plug in given conditions and solve. And then fifth, we're going to write our answer with units. As a complete sentence. And when you plug in the given conditions, I would say plug them in with the units, because then as you simplify the numbers, you can also kind of simplify your units, and it will help you make sure that your final answer has the correct units, because some of these units are weird, like feet cubed per minute or whatever, and that's kind of a weird. I think that these might be a little bit outside of what our common sense would help us figure out for the answer. So if you plug in your numbers with their units, it might be a little bit easier to solve things. Okay, so here is our second example. It's going to be a little bit less easy than that first one, so we're actually going to have to go through this process. So we're going to go ahead and annotate the problem. So we have a pebble is dropped into a pond. I really should have said the word circular here, because there's not enough information in the problem for you to understand that's what they're saying. So it says the radius of the outer ripple is increasing at a rate of 1 foot per second. So the radius, and when the radius is exactly 4 feet, what is the rate of the total area that's disturbed or is changing by? So we've kind of underlined things. Here's my pond. And you're throwing a little pebble in there, and we've got this like ripple effect, right, that you can picture. And so it's saying when the radius is 4 feet, what is the total area of the disturbed water? And then we do know that the rate is increasing 1 feet per second, the radius of that outside ripple. So this ripple that's moving out is increasing at a rate of 1 foot per second. So a few formulas that we should write down. We know that the area of a circle is pi r squared. And we know that the rate that the radius is changing with respect to time is that it is increasing 1 foot per second. So this is the change in the radius with respect to time. All right, so we are trying to figure out the rate that the total area of the disturbed water is changing. So we are trying to find the rate that the disturbed area is changing with respect to time. And we want to find this out when the radius is 4 feet. So I'm just going to say when r equals 4. Okay, so that's all the information I believe that the problem gave us. So now at this point we found the equation, now we're going to find the derivative of the equation. So the rate that the area is changing comes from when we find the derivative of the area. So I'm going to say the derivative of A is just 1. So 1 dA dt equals, the derivative of pi r squared would be 2 pi r times dr dt. And dA dt is what I'm trying to solve for, and then these are the things that I have numbers I can plug into. So dA dt is 2 times pi. My r value is 4, and I'm going to go ahead and include my units there, 4 feet. My dr dt is 1 foot per second. So if I multiply all those things together, I'm going to see that the area with respect to time is changing. 2 times 4 times 1 is 8, and then I'm going to stick the pi on there. And feet multiplied by feet per second would be feet squared per second. And so the area of the disturbed water, if we look at as this ripple is continuing further and further, the area of that water, when the radius is exactly 4, is increasing at a rate of 8 pi feet per second squared. And that's kind of a weird way to phrase this answer, so I'm going to go ahead and just type that in my calculator and say that that rate is approximately 25.133 feet squared per second. And then I'm going to go ahead and write my sentence to kind of interpret what this means. So I'm going to say, when the radius of the ripple, of the outer ripple, is 4 feet, the area of the disturbed water is increasing by 25.133 feet squared per second. All right, air is pumped into a spherical balloon at a rate of 4.5 feet cubed per minute. Find the rate of change of the radius. So rate of change of the radius when r equals 2 feet. How is the surface area changing at the same time? So a spherical balloon, that's not the normal shape of balloons, by the way. They're usually not spheres. They're kind of like cones-ish, kind of. So a spherical balloon means that that balloon is like a perfect circle, like a 3D circle. So if we look at this problem, we know that we need the volume of a balloon, because that's what it's describing right here. If air is being pumped into the balloon, we're talking about a volume that's changing right here. And then they're also asking about the surface area changing. So if we needed to look up some formulas on Google, and I would guess we would because you probably don't have these memorized, we would be looking up the volume of a sphere and the surface area of a sphere. So let's go ahead and write down those formulas. Actually, I forgot about drawing the picture. Let's go ahead and draw a picture. I don't know how to draw a sphere. There's our little sphere. And look, it's a balloon. All right, so air is being pumped into the balloon. I don't know how to draw that. So anyway, let's go ahead and find the volume. So volume, if you Google the formula, it's 4/3 pi r cubed. Surface area of a sphere is 4 pi r squared. So here are the things they're telling us. They're saying that the volume, air is being pumped into this, so there's a volume right here, and the change in volume with respect to time is 4.5 feet cubed per minute. They want to know the rate of change of the radius. So dr dt is something we're going to be finding. We don't know what that is. When the radius is 2, they did give us that specific information. And they also want to know how the surface area is changing at the same time. So the change in the surface area with respect to time is, we're not sure, but we do know we're checking this when the radius is 2. Okay, so those are the things it looks like we already have. We're considering what we need. Okay, so I know my volume is this stuff. I know that when I take the derivative, that whatever my derivative is going to equal 4.5. And so I'm going to go ahead and take this equation and take the derivative of it, since I already know what the derivative should equal. So the derivative of v would be 1 times dv dt. And if I do the derivative of this, I'm going to have 3 times 4/3 pi r squared times dr dt. And I'm going to go ahead and clean this up a little bit. So 3 times 4/3 is just 4. So I have 4 pi r squared times dr dt. And I know that this derivative equals 4.5 because dv dt equals 4.5, and I'm including my units in here. So 4.5 feet cubed per minute. And dr dt is one of the things we're solving for, but we do know that we're solving for that when the radius equals 2 feet. Put all my units in here. So I have 4.5 feet cubed per minute equals 4 pi times 2 feet squared dr dt. Okay, so now I know that I need to get dr dt all alone because that's one of the things I'm solving for. So I can just divide by everything that was on this side. So 4.5 feet cubed per minute is going to divide by 4 pi And I'm just going to go ahead and square both of those things. So 2 squared is 4, and then feet squared. That equals dr dt. And so dr dt, I can go ahead and type this into my calculator. Okay, so dr dt, I'm going to write that this is approximately. And if I round it to 3 decimal places, the 89 is followed by a 5, so that tells us to round up to 90. So 0.090. And we had feet cubed per minute divided by feet squared. And so the feet squared are going to cancel out with 2 of those and leave 1, so we're going to say feet per minute. Okay, so that was one thing we needed to solve for, and dr dt is the rate the radius is changing. So as air is being pumped into the balloon, the radius is changing by 0.090 feet per minute when the radius is 2 exactly. That's what that part is saying, and we're going to write that in a sentence, of course, in a second. So I'm going to go ahead and see if we can figure out this other rate of change we needed. So we're saying that ds dt is what we're solving for. So I'll go ahead and take the derivative of this equation. So the derivative of the surface area would just be 1, right? Because that's considered to be one variable. That's not the product rule. I just used 2 letters to describe one thing. So the derivative of the surface area would be 1 dsa dt. And then if I do the derivative of this side, it would be 2 times 4 is 8 pi r times dr dt. So dsa dt equals 8 pi. My radius is 2 feet. My dr dt I just solved, that's 0.090 feet per minute. Ooh, it's hard to fit in. So now I'm just going to go ahead and take 8 pi times 2 times the answer I just got up here. And the surface area is changing by 4.5, and this is feet squared per minute. Okay. So we're going to say when the radius is 2, the radius is changing, or I should say increasing. Well, if we're changing by a positive number, then we'll know it's increasing. So I can say it's changing by 0.090 feet per minute, and the surface area is changing by, or you could write increasing by, 4.5 feet squared per minute.